Welcome, everybody. Today, we are very happy to have Ofer Aharony from the Weizmann Institute, and he will tell us about the gravity interpretation for the Bethe ansatz expansion of the n=4 Supraconformal superconformal index. Please.
Okay, thank you very much for the invitation to speak here. Let me start by apologizing that this talk has nothing to do with integrability. I mean, even though the words Bethe ansatz appear in both topics, but as far as I know, there's no relation. I mean, maybe we can figure out some relation during this talk, but I mean, I don't know of any relations to integrability, but I was still invited to speak here, so I'll still give the talk. And the other comment is that since it is a Blackboard talk, then really please feel free to stop me with questions at any time. And in particular, please let me know if the handwriting is not clear or if the sound is not good or anything like that. But also, of course, any physics questions at any time are very much welcome. So this talk will be based on this paper that appeared in April and also on work in progress. And this is in collaboration with Francesco Benini, with my student Ohad Mamroud, and with Paolo Milan. So let me start with the motivations. So the main motivation is to learn more about counting black hole microstates. So we know that black holes have some entropy, and one of the challenges for a theory of quantum gravity is to be able to give that entropy a statistical mechanics explanation in terms of the logarithm of some number of microstates of these black holes. Of course, we'd love to do that for black holes in flat space, but in flat space we don't have any non-perturbative theories of quantum gravity, so we don't really have any way to answer that question so far in flat space. Our next best case to hope for is to try to count these black hole microstates in anti-de Sitter space, where we do have in principle a mapping of these states to states in some conformal field theory. And in low dimensional ADS, like in ADS3, we can actually do that because we do know how to count states in two-dimensional CFTs in general at high energies. But in higher dimensions, even that we don't really know how to do, because in generic 3- and 4-dimensional conformal field theories at strong coupling, I mean, we also don't really know how to count the density of states. So even that is still too difficult. So the case that we do actually maybe hope to do is not to count all the black hole microstates, but just to count BPS black hole microstates. So to look at black holes that preserve some supersymmetry, but would still have a macroscopic horizon, so that they still have some macroscopic entropy. And then we can hope to match the counting of those black holes to counting some supersymmetric states in the corresponding field theory. And in particular, today, I'll discuss the specific case of counting the 1/16th BPS states, or the 1/16th BPS black holes in type 2b string theory on ADS5 cross S5. And those are, of course, dual to 1/16th BPS states in the n=4 super Young-Mills theory on S3. So I'll discuss the mapping between the super Young-Mills theory on S3 and global ADS space. And there should be a one-to-one mapping between the black hole microstates here that preserve some supersymmetry and the states of this super Young-Mills theory at strong coupling. Now, the advantage of looking at BPS states is that those states, in some sense, we do know how to count also at strong coupling, because we can count them using the superconformal index. So there is what's called the superconformal index, which I'll discuss in detail a bit later, which counts all the 1/16th BPS states. So it's given by some trace over -1 to the f, and then various quantum numbers of these states. And using the superconformal index, we can hope to count all the BPS states and match that to the entropy of these black holes. In particular, the black holes in ADS5 cross S5 are characterized by a mass. They're characterized by two angular momenta in the ADS5. And in the n=4 super Young-Mills, we have an SU4R symmetry. So they're also characterized by 3 R charges in the cartan of this SU4R symmetry. And in principle, we can ask for the entropy as a function of all these charges. So count really the black hole microstates with any given charges. Of course, for BPS black holes, the mass is determined in terms of the charges. So the mass is not an independent parameter, but we can count black holes. In principle, we should be able to build black holes with all these charges. And we'd like to really match in detail the entropy of given charges to the index. Now, in the index, we don't really count states with a given charge, but the index, we count states with some given chemical potential. So the index depends on some chemical potentials, tau and sigma for the chemical, for these angular momenta, and some chemical potentials that I'll call delta 1 and delta 2 for the R symmetry charges. So it counts all the 16th BPS states with some weights. And in principle, that should be related by a Alexander transform to the counting of the black hole microstates.
Sorry, could I ask?
That's all very nice.
Here.
Yes.
So why the microstates all have the same quantum numbers as the solution itself? So in principle, it should hold in average, right, in thermodynamic limit. Right, if you have some quasi-classical
well, for every value of the charges, we have a black hole with these charges, and then we believe that the entropy of the black hole with these charges really counts for us all the possible microstates with those charges.
Yeah, but more basically, so if you have some state in like thermodynamic system with given quantum numbers, that doesn't mean that all microscopic states have the same quantum numbers as this macroscopic state. It's not just in average.
Right. Yeah. Okay. I mean, there could be some smearing, of course, but in the thermodynamic limit, where it's a larger number of states, I mean, I think that variance should be relatively small. So yeah, I mean, of course, we're not really going to focus on fixed charges, but just the functional form of this as a function of the charges.
So it is 1 over n exact, or what's the precision?
Well, so we'll see exactly. Yeah. So I want to make this mapping as precise as possible. So we'll see what we can and cannot make. But in terms of counting the microstates, there are actually more serious problems than what you mentioned. So there are two more serious problems here with trying to really read off the black hole microstates from the superconformal index. One big problem is this -1 to the f, which tells us that in principle, the index counts 1/16 BPS states, but it counts them in general up to sign. So there could be some cancellations between different 1/16 BPS states. And indeed, when people first computed the superconformal index, I guess more than 15 years ago, for specific values of these chemical potentials, they did not reproduce the black hole entropy, but they found much fewer states. And now it's realized that that was because, indeed, for those specific chemical potentials which they used, there were actually cancellations here between many different states. And later, the computation was generalized to general complex chemical potentials, and then these cancellations went away. And again, I'll describe exactly what was found later in this talk. But that's obviously one limitation in terms of using the index to learn directly about the black hole macrostates. And the other limitation is in the index, we can really only turn on chemical potential for 4 of the 5 charges of the black holes. So in that sense, also, the index only carries some limited information about the precise charge distribution of the black hole. I mean, it smears them in one direction, but still, I mean, that's what we can do. And of course, even though we can't reproduce exactly the BPS, the spectrum of the BPS microstates, we can, of course, learn a lot about them from this index in particular. Even if we can plug that into we can plug these states and see what they contribute to the index and see if we can reproduce that. And in many cases, that was done. But the mapping in this direction, in this case, is not completely precise. So in order to get a somewhat more precise mapping between the two sides, I mean, our goal here will really be to do ADS CFT very precisely. We can actually find a different mapping of the superconformal index to gravity, which can be done more precisely. So the superconformal index, on one hand, it's a sum over BPS states, but on the other hand, it can also be described as a partition function of the n=4 theory on S3 cross S1 with specific boundary fields on the S1. So that's just the general statement that the superconformal index is just some glorified thermodynamical partition function. And as always, we can replace that by a Euclidean path integral, in this case on S3 cross S1, where we put the theory on S3 with some specific background fields that preserve supersymmetry and take into account these chemical potentials. So this is an exact equality. And the partition function on a Euclidean S3 cross S1, of course, that we also know how to translate to the gravity side by the ADS CFT correspondence. So we should just look for Euclidean solutions that have this S3 cross S1 boundary and that have the appropriate background field corresponding to what we have here. And then here we should really be able to find a precision match between the superconformal index and the gravity contribution from all these Euclidean supersymmetric solutions that have specific boundary conditions. So in principle, this can be done very precisely. But in trying to do this matching, it turns out that there's also a subtlety. As we'll see, to do this matching, we have to introduce here background fields that take complex values. So also the boundary conditions that we'll need to find for our ADS solutions will take complex values. As usual, sources that we turn on the field theory side, like background fields, translate into boundary conditions for our gravity solutions in anti-de Sitter space. And in this case, it looks like we need to look for solutions with boundary values of the fields, which are complex, and it's not so obvious what that means. So that will be a subtlety that we'll have to deal with if we want to do this mapping more precisely, and which we'll discuss in detail in this talk. Now, the superconformal index, one nice feature of it is that we do know on field theory how to compute it very precisely, and in particular, one method to compute it precisely, even at finite n, and also in the larger limit, is what's called the Bethe ansatz method, which I'll describe. So that writes this index as a sum over some solutions to some Bethe ansatz equations. And each solution contributes some specific number. So we can rewrite this superconformal index as this sum over solutions. And then the main question that I'd like to ask in this talk is, can we relate this sum over solutions, which we find on the field theory side, to some sum over solutions on the gravity side, which in this case, of course, would naturally be a sum over solutions of Euclidean gravity with some specific boundary conditions. So a priori, it's not obvious that we have to map a specific sum. We know that the full partition functions match between the two sides. It's not obvious that a specific way of writing this partition function as a sum should also be translated into a natural sum on the gravity side. But at least in some cases, it's obvious that it should be possible. Generally in this sum, as we'll see, in many cases, there's just one solution that dominates that sum, and then that solution, at least, we expect to correspond to some classical solution on the gravity side that will dominate the partition function. And for different values of the parameters, there are different solutions here that dominate.
May I ask a question?
Yes, please.
How you define intrinsically the superconformal index?
So I'll discuss that in a few minutes. So this is just the very general introduction. I'll get into all the details in a few minutes, and then you can ask that question. But yeah, for now, the index is going to be a very specific trace over states and so on, which I'll define in a few minutes. But now I'm just mentioning that we can write that state as a sum over discrete solutions. And that's the question I'd like to ask in this talk is, can we translate this sum over solutions that we get on the field theory side for this partition function to a sum over some Euclidean solutions here, taking into account this caveat that it's not completely obvious which solutions we want to talk about, given that these are going to be solutions with some complex boundary conditions. So this is the general motivation for this talk. And the outline for the talk is the following. So we already finished with the general motivations. So in the first part of the talk, I'll discuss the superconformal index and how we compute it using this Bethe ansatz method and write it as a sum over Bethe ansatz solutions. And in particular, I'll discuss what these solutions give in the large N limit, which is relevant for the mapping to classical gravity. And we'll see that it gives both perturbative contributions and also some non-perturbative contributions exponentially small than n that can also be completely controlled from the field theory side in this case. So that will be the field theory side. Then we'll discuss how to reproduce that sum in the gravity side. The leading contribution on the gravity side will just be classical contributions coming from various Euclidean black hole solutions. But we'll see that if we naively take them into account, we'll encounter some puzzles. And in order to resolve these puzzles, we'll have to discuss also the non-perturbative contributions and how those are reproduced on the gravity side. And we'll see that those will come from wrapped D3-branes on the gravity side. And once we take into account all of these different contributions, we'll see that eventually we do find a precise match between the computations on the field theory side and on the gravity side, which is really a very, if you want, it's precision ADS CFT. We'll really be able to match the two sides with great accuracy. And I'll end with a summary and some future directions. So are there any questions about the general motivations before I start getting into the details?
I just have one quick question, Ofer.
Yes, please.
How would, can you give just an example of a few of the operators that would generate this 1/16 BPS black holes? How do they look like?
Well, in the free field theory, it's easy to build them. It's just some of the so let's see. And basically, there are combinations. So there's one of the fermions in the theory, I think, and one of the scalars in the theory that satisfies this BPS condition, and then also say, I think, two derivatives in specific directions. So basically, you just construct strings of these specific of products of the specific scalar and fermion adjoint with the various derivatives and so on. And in the free field theory, all of those are 16th BPS states. And then for the index, of course, it's enough to count them in the free theory because the index is independent of the coupling. We don't know which of these states may be lifted in pairs when we turn on the coupling. So that's a question that's much more difficult. But to compute the index, all we need to know is the 1/16 BPS states in the free theory, and those are easy to identify. You just need to look at which operators in the field theory obey the appropriate BPS condition.
Let me just ask something. So, but do I need to take these operators with a charge of order n square, or
yes. So of course, when we take, so we'll compute the index for general n, but of course, eventually we want to take the large n limit, and in the large n limit, the contribution will be dominated by states like this, which have charges of order n squared. Definitely, yes. of course, also the black holes that we match to, these black holes all have angular momenta and charges that are of order n squared in units of the minimal charges.
But these operators, they will generically all get an anomalous dimension, right? So their dimension.
No, well, the ones that stay 1/16, I mean, if they're 1/16 VPS, then they won't get an anomalous dimension unless we have sort of pairs of 1/16 VPS multiplets, one bosonic and one fermionic, with the same quantum numbers that can join together to become a long multiplet. Yeah. So some of them may join together to become a long multiplet, but those don't contribute to the superconformal index anyway. I mean, so those will just cancel in the superconformal index. So any multiplet that contributes to the superconformal index, its dimension will not be corrected, and it will have exactly the same energy also at strong coupling. I mean, that's why the index is useful for counting these black hole microstates.
So is there a simple way of describing those, the ones that are not going to?
Well, so we don't know. I mean, so in the index we really just count all of the states in general, and we don't know which. So for some quantum numbers, we may see that there are 8 bosonic states and 7 fermionic states, so there's a net contribution of 1 state, but we don't know exactly which one state that is. I mean, so in that sense, I mean, we don't have that information on exactly which state survives. Of course, for other quantum numbers, there may be only bosonic states or only fermionic states, and then we know that all of them survive also to strong coupling. So that already depends on the details.
Do we at least know some family of such states that don't receive anomalous dimension, like some examples, like some determined?
Yeah, so I don't know. I mean, I haven't studied that. I mean, I know that there are some people that have looked at that, but I haven't looked at that myself. I mean, again, in this talk, actually, after this introduction, I'm not really going to go back to the black hole microstates at all. And all I'm going to discuss here is just this superconformal index and its mapping to the Euclidean partition function. So that is a very precise statement that we can make. But yeah, going back to the black hole microstates, as I discussed, that's much more subtle because of all these issues that we mentioned. So, and I don't really have anything new to say about that.
Okay, cool. Thank you.
Any further questions?
Yeah, but typically we should think of these as determinant operators then, essentially, rather than trace operators, because you're going to want to.
Well, you can start by constructing them as traces, but of course the traces have various conditions and so on. I mean, so yeah, we're really computing the exact index for finite n, and also then we'll take its large n limit. But yeah, obviously we can't think of them when the charges of order n squared. We can't think of them as single traces or double traces and so on. I mean, all of these. That's of course not a good basis anymore. So yeah, whatever we get is what we get. I mean, we're really going to count the states precisely and see what we get.
But I'd want to start with some very big determinant operator and then maybe sprinkle it with some impurity.
Well, so again, you don't even need perturbative. I mean, because this index is independent of the coupling, you can just really count free field theory operators. So we're just going to count free field theory operators. From them, we can
sure, but you know, but I think a lot of people
some of them will survive, some will not, but the index will be the same. So
sure, but I think Pedro's questions were because a lot of people here have written down a lot of these operators and thought about them quite explicitly, and so yes. I guess. So, for example, people like the trace Z to the J operator.
Sorry, it's not determinant, right? It will be determinant to the N, right?
Right. Yeah. These are much more complicated than determinants. Yeah, that's right.
Of course,
but even the determinants are not a good basis for those states, and we don't really have a good basis for those states. I mean, and of course, if they were half VPS, they would just be determinants to the power n and so on. But these are 1/16th VPS. I mean, so we don't.
Yeah. Really so what I wondered is whether if you start with one of those half VPS ones, then add a little impurity.
Yes. Yeah. So that's one way to get these things. Yes. But those would not be the generic ones, of course. Those would still have an entropy of order 1 in the large limit. Well, we really want things whose entropy goes like n squared. So those are generally very far from even from 1/8 VPS states. I mean, as you know, the entropy of 1/8 VPS states is still not large enough to give these entropies. Okay. So these are really different from the 1/8 VPS and certainly from the half VPS states. And those would not give you a good intuition for what generic states like this look like.
Okay, thanks.
Okay, so what's the definition of the index? So the index can be thought of, the superconformal index in principle is just some Witten index. I mean, so we just want to count all the states in this field theory on S3, or equivalently, we can count operators, and by the state operator correspondence, equivalently, we can count operators, and we want to count them with a weight, which is -1 to the f, and then either minus beta times this, just like in the Witten index, and this guarantees that we're only going to count states that are annihilated. So we're going to choose some specific supercharge Q in the n equals 4 theory. And this form guarantees that we're only going to count states that are annihilated both by Q and Q bar. So these will be the states that we call the 1/16th BPS states. So this would be a general Witten index. And then on top of that, we can add various holonomies for various global charges that these states can carry. And in particular, we can add holonomies for any charges that commute with this supercharge that we have. So in generic for the n equals 1 theory, then states would be characterized by 2 spins, J1 and J2, and which in the SO4 rotation group of the S3, and by some R symmetry. And then there would be these charges J1 plus 1/2 R and J2 plus 1/2 R that commute with the supercharge Q that we choose, so that we can add them in and still preserve this property that states that are not alleviated by Q and Q bar will cancel out in the index. And on top of that, in general, we can add any flavors that commute with this supercharge. So this would be the general form of the superconformal index in a 4D n equals 1 theory. And again, this by construction, this only counts states that are annihilated by Q and Q bar. And one can prove that it's independent of any couplings, so that we can compute it either at weak coupling or at strong coupling. So this would be the index in a general 4D n equals 1 theory. In the specific case of the 4D n equals 4 theory, then as I mentioned, instead of the R chart, we really have 3 R symmetries, R1, R2, and R3. In the cartan of the SU4 R symmetry, you can write the n equals 4 theory, say, in terms of 3 chiral multiplets, phi1, phi2, and phi3. And then you can choose the R charges of these states to be 2, 0, 0, say 0, 2, 0, and 0, 0, 2. So that's the normalization that I'll be using for the charges. And then the index in the n equals 4 theory, we can write it in the following way. So we can add 2 extra charges that also commute with this supercharge. So the general index can be written in this way. So it has holonomies for these combinations of the charges. Then there's a holonomy y1 for 1/2 R1 minus R3, which also commutes with the supercharge that we're interested in, and y2 to the power of 1/2 R2 minus R3. So this is the precise definition of the index that we want to compute. And again, on general grounds, this is independent of the coupling. So we can compute it exactly already in the free theory. And the reason that I chose the specific form of the holonomies that appear here in the index are that with this choice, all of the charges that appear here are all the integers. So that if we write these holonomies P as e to the 2 pi I tau, then we have a periodicity under tau goes to tau plus 1. I mean, this is a single valued function of P. And similarly, if we write Q as e to the 2 pi I sigma, then we have a periodicity in sigma. And we're also going to write these yi's as e to the 2 pi I delta I. And so this index is periodic in all 4 of these variables. So we can write this index as a function of tau, sigma, delta 1, and delta 2, which are these 4 holonomies that commute with the supercharge that we're interested in. And it's periodic under all 4 of these holonomies. So that's what we would like to compute. So this is the general formula for the index.
Sorry, the power in the y's is a little unclear.
Sorry, this is yi equals e to the 2 pi I times delta I.
No, so in the index.
Oh, sorry. So here it's 1/2 R1 minus R3, and here it's 1/2 R2 minus R3. Yeah, sorry, that this is a bit small because I didn't have space. But these combinations R1 minus R3 are always even, so that's why this power is an integer. For all the bosonic states in the theory, the R charges are even in this normalization, and for all the fermionic states, all the R charges are odd, so that for any given state, these differences are integer, and the index is periodic in these variables. So this is the general equation that defines the index. And now we'd like to compute it. And well, there are 2 general ways to compute the index in supersymmetric theories, and both of them give exactly the same formula. One way to count the index, which I already mentioned before, is just to count the states in the free theory. So we can just count a generic state that we can write down from the fundamental fields of the n equals 4 theory. So we can take a product of all these basic fields, the scalars, the adjoints, and the gauge fields. And then we have to impose on top of that a projection onto the states that are invariant under SUN. Of course, we want to only count gauge invariant states. So in that formalism, each of these states comes with some character or some representation of SUN, and we multiply all these characters. And eventually, we need to have an integral over the SUN gauge group to project onto the gauge singlet states. So that's one way of writing down an explicit formula for this trace, just by explicitly counting the BPS states. The other way to compute this index is by localization. So as I mentioned, this index is equivalent to a partition function on S3 cross S1 when we put the theory supersymmetrically on S3 cross S1. And in that language, we can compute it via localization. So we can localize to specific field configurations, where it turns out that in these field configurations, all the degrees of freedom are fixed except for the holonomy of the gauge field on this S1. So there's some holonomy matrix U of the SUN gauge field on the S1. So in that language, the partition function becomes an integral over this holonomy matrix on the S1 of some specific expression that comes from performing the path integral over all the other modes. So these are the 2 general methods of computing the index. And both of these methods give the same formula. So let me write down this formula here. So this is the general formula for the index of the n equals 4 super-Yang-Mills theory. So the index is written as an integral over an SUN holonomy. So I'll denote by Zi's the eigenvalues of this SUN matrix. So we have this SUN matrix. We can diagonalize it to this form Z1 up to Zn. And we can write each of these Zi's as either the 2 pi I ui. Of course, they're all phases that live on the unit circle. And then the index is given by an integral over this matrix, which in this case is just an integral over the Zi's, each of which lives on the unit circle. So it's an integral over n-1 copies of the unit circle. And the expression that's being integrated is this specific function, which is a bit complicated, but it's completely explicit. So we have here a product of various elliptic functions. The arguments of these elliptic functions are these uij's, which are just the differences between the logs of these eigenvalues of these SUN matrices. And otherwise, their parameters just depend on these chemical potentials, tau, sigma, delta 1, and delta 2. And this theta 0 is a relative of the Jacobi theta functions, which in particular can be written in this product form very explicitly. So we can just plug in this product form and write this index as an integral over a product of lots of factors of this type, which again, you can get either from localization, where it comes from the one-loop determinants, or you can get it just from counting states, where it just comes from putting in the partition functions for the various states in the theory. So this is the precise expression for the index of the SUN n equals 4 theory. And this is what we'd like to compute and then compare to the gravity side. So are there any questions about the expression? Again, the details of the expression will not be so important.
Sorry, Ofer, I can't see read it very well. They're all the same theta function.
They're all the same theta function, just for different values in this way of writing it, it's all the same theta function, just with arguments that are either uij or uij shifted by some chemical potentials, or uji and uji shifted by some chemical potentials. But yeah, you know that. I mean.
Yeah, I know that. Yeah, oftentimes one uses a different function.
Right. Yeah. So of course you can write it in many different ways by using lots of Jacobi theta function identities. But I mean, this is, I think, the simplest way of writing it, where you only need one Jacobi theta function, and it's explicitly just this ratio of infinite products.
I see.
So next, we'd like to compute this index, and in particular to compute it in the large limit, but also in general. And there are many different methods to compute this index.
Could I have a naive question?
Yes,
so
please.
If it's in free theory, can you also compute without any localization? Computing
yeah. So that's the way it was originally computed in the paper of Kinney et al. I mean, already in 2005. They computed it just by counting states in the free theory, and they get exactly the same expression. So you can use either localization or just counting states in the free theory. It gives you exactly the same answer.
Sorry, Ofer, is it written like this in any paper?
In this form?
Yeah.
Well, this form I took from one of the papers of Francesco and his collaborators, but yes, it is. Okay, any further questions about this expression? Okay, so then we'd like to compute it, and there are
maybe you will comment on that later. But my question is essentially, what are the range of value of sigma and tau and deltas? So that
right. So that's a question already about the original, the way that I wrote the index. I mean, so a priori, you may start from imagining that if you want to have some real holonomies for all these background fields, but eventually we're going to make them complex. I mean, so they have to obey that their imaginary parts have to be certainly non-negative or even positive for the sum that's written in the index to converge. So all of them, so sigma and tau need to have positive imaginary parts, while delta 1 and delta 2 are essentially unconstrained. I mean, so in general, this expression on the field theory side makes sense for any complex values of sigma, tau, delta 1, and delta 2, as long as they obey these two constraints. And again, it's periodic in all of these 4 variables.
Another question. So in matrix models, normally these types of expression you can write it in by a determinant of one-dimensional integrals. Is it true here or not?
Yeah. So here I don't know if it has. I don't know if it can be written in this way. This is the simplest way I know of writing it. Okay. So how do we compute this index? So there are different ways to compute it. In particular, many people have computed it in the large limit by various saddle point approximations, either by looking for saddle points along the axis of integration, or many people in particular in the King's College group have computed it also by analytically continuing these expressions and looking for complex saddle point at large n. But the method that I'll focus today on for computing it is really the the most exact method that we have for computing it, which is really, in some sense, just a brute force evaluation. So we have here this product of n-1 contour integrals on the circle. And in general, if we have some pole of this function, so this function, of course, has lots of poles as a function of its arguments. I mean, it has poles whenever one of these factors vanishes. So there are lots of poles inside the region of integration. And if we have discrete poles as a function of all n-1 variables, then we can just use the residue theorem and just write the result of the integrand of the integral as a sum over the residues of all these different poles. Again, and this is not a one-dimensional integral, but it's an n-1-dimensional integral. But still, if you have discrete poles for all of these integrations, then you can just write it as a sum over all these poles. And that's essentially an oversimplification of what's called the Bethe ansatz method for computing it. So schematically, what you do in this method, you just look for the poles of this expression, and you want to write down the index as a sum over these poles. So in this method, the index is written as a sum over solutions to some equations, which are called the Bethe ansatz equations, which are essentially the conditions for having a pole in all n-1 integrations here. And for each of these poles, you have some expression, which is basically the residue dressed with some Jacobian. I mean, so these solutions are some UI star, some specific values for these holonomies. And then you have, for each one of them, you have the residue, which will be some function of sigma, tau, delta 1, and delta 2. Now, this Bethe ansatz method actually works best for the case where these two chemical potentials, tau and sigma, are equal. So from now on, I'll only discuss this case where these chemical potentials are equal. And in that case, there's a very simple form for these Bethe ansatz equation solutions. So in that sense, the Bethe ansatz equations that determine where we have poles in all these integrals take this form. So again, it's some product of theta functions that has to be satisfied. So we have these QIs for I going from 1 to n-1. So we have here n-1 equations in these n-1 variables, which are the UIs. And each of these equations is a product of theta functions. And in general, if we find discrete solutions to all of these equations, then the index is just given by the sum over all these solutions of some specific expressions whose details will not be so important for us. So this is the essence of the Bethe ansatz method. Now, this method assumes that the solutions to these equations are discrete, so that we really have discrete poles inside the region of integration. That's not precisely true. So there are going to be probably, so it seems that there are also some solutions that are not discrete, and then they give extra contributions that do not take precisely this form. But in this talk, I'll only talk about the contributions from discrete solutions, which we do know how to compute.
Do these Bethe equations come up in some other integrable systems?
Yeah, so that's a very good question, and I hope that you guys know about that more than I do, because I don't really know. I mean, I don't know any specific system that gives exactly these equations, but maybe one of you guys does know such a system.
So why are
obviously they resemble.
Why were they originally called Bethe equations?
So yeah, so of course they resemble those equations, but yeah, I don't know if they appear, if there's any specific other system where they appear. It would be very interesting if there is, but yeah, but I don't know any.
So who called them Bethe equations first?
Yeah, that's a good question. I don't really know the history because I joined the subject after that. So yeah, I'm not
well,
really
they do like Bethe equations. It's fine, right? It's not illegal. What are the? Could you remind what are deltas again?
So these deltas are the chemical potentials for the flavor symmetries. I mean, so we had these y1 to the power 1/2 r1 minus r3 appearing in the index, and this y1 was e to the 2 pi I delta 1, and similarly for delta 2. So these deltas are just the chemical potentials for the flavor symmetries, and this tau, which is equal to sigma, is essentially the chemical potential for the angular momentum. So these are the equations that we need to solve, and if we only had discrete solutions to these equations, then we could really compute from them the full index, which would just be a sum over these discrete solutions. Now, as you can see, these equations have the nice property that they only depend for a specific I, they just depend on these uij's, which are the distances between the eigenvalue I and the eigenvalue j. So we can, if we take the log of this formula, we can sort of write this Bethe ansatz equation in the form of a sum over all the j's of some v prime of uji. So it looks like we have these eigenvalues, and we just have some condition that the force between these eigenvalues, say coming from some pairwise potential between the eigenvalues, has to vanish. So schematically, that's what these equations are, but albeit with a rather complicated potential between the eigenvalues. But in principle, that's all that we have here. So those are the equations that we need to solve. The one interesting thing about these equations is that, I mean, there's an obvious periodicity of ui going to ui plus 1, just because they originally came from these holonomies of sun. But it turns out that these equations are also invariant under ui goes to ui plus tau. So when we look for the solutions, we should really look for solutions that just sit in some torus with a modular parameter tau, because we have this periodicity. So we have to find some place to put these n eigenvalues of this matrix where the n eigenvalues all sum to 0 because we're in SUN, and where all the forces between them vanish. So this is the mathematical problem that we need to solve in this approach in order to compute the index. Now, solving these equations in general is very complicated, and indeed we don't really know how to solve them.
Can I ask a question? So,
yes, please.
Would this way of writing the index as a sum over solutions, would it have an interpretation from just in the free theory when we are just counting operators? Are they integers?
Yeah, that's a very good question. Yeah, I don't know. Good. Yeah, it's a good question. I don't know any obvious interpretation. I mean, again, it just comes from these residues in these formulas, and yeah, you're right that these residues, we can interpret them potentially as coming from some specific operators. I mean, which would cause these zeros. So yeah, it's an interesting question. I don't know the answer.
So sorry, and can you like just give some idea of this continuous? Because if it's sum over poles, then why would they not be discrete? Are there some branch cuts after you?
Yeah. So when you try to solve these equations, it turns out that so we have here n-1 equations and n-1 variables. And again, if these solutions just had discrete solutions, then it would just be a sum over these discrete solutions. But yeah, it turns out that the space of there are also continuous families of solutions. I mean, so in this higher dimensional space, you could have a surface of zeros instead of just discrete zeros. And then it's more complicated to put the contribution to this n-1 dimensional integral that comes from these other surfaces. So that's still part of our work in progress, is to understand the contribution from these other
but that doesn't mean that when you compute by residues this integral, at some point you find branch cuts.
Well, I don't think it's branch cuts. I mean, these are all analytic functions of the use. I mean, it's just that you find that there are zeros that are just not codimension n-1, but they're over a lower codimension, so that it's.
But say if I take one integral z1, right? It is
yes. Yes, of course, for one integral that can't happen, but it happens when you have these multi-dimensional integrals. So you have these higher dimensional spaces of solutions, and then you just have to use more sophisticated method. I mean, of course, for generic equations this won't happen, but these equations have some very special properties that, I mean, essentially some solutions overlap with each other, and that's why you get these types of behaviors.
Another question: if you take another gauge group, will it kind of possibly?
Yeah. So again, people don't really know how to solve these equations. I mean, so they were analyzed in detail for SU2 and for SU3, which are two cases where you don't have these continuous solutions. But then when people went to SU4, it was found that there are also continuous solutions in addition to these discrete solutions, and the full set of solutions, again, it's not really known. So for the purposes of today's talk, again, I don't mean if you guys have any ideas for how to solve these equations in general, then that would be great. But today I'll just discuss the contributions from some specific known solutions. So there is actually a very simple set of solutions to these equations, which are just given by distributing the UIs evenly along some line in this on this torus. For instance, if you distribute them along the line in this way, which is again is periodic because of this tau periodicity, then it's obvious that when they're equally distributed, then all the pairwise forces between them cancel. So this is obviously a solution to these equations independently of the precise form of this potential or of these equations. So a solution like this, where the UJs are just given by some constant U0 plus j over n times tau, essentially, that's guaranteed to be a solution just from the general form of this equation. So that's
yeah. Ofer?
Yes, please.
Did you say that SU3 there is no continuous? What did you say? I thought already for
yeah,
SU3.
I think that, if I remember correctly, that for SU3 there's no continuous solution. That's not true. I mean, maybe I'm wrong.
SU2 for sure not. But I thought already at SU3 you start saying that. I'm not sure.
Maybe you're right. Yeah. Sorry, you may be right. Yes. Okay. Sorry. Right. Maybe for SU3 you're already right that there is. Yeah. Okay. So I retract.
Sorry. What do these solutions mean for the index?
Again, each of these
to some real operators, or
yeah. So well, there's no direct
legitimate operators.
There's no direct interpretation. So that was the question that Pedro asked before. I don't know any direct interpretation of these solutions for the form of counting over states. I mean, again, the index comes from summing over all the states, and that sum can be replaced by this sum over solutions to these equations. But I don't know any direct way to map specific solutions and their contributions to specific operators. I mean, that it would be nice if there is such a way, but I don't know how to do that.
So the meaning of this continuous family of solutions, that parameter is physical or not physical?
Well, the continuous solutions, I mean, they also give contributions to the index, just their contribution is more complicated. It's not just reduced, so you have to use slightly more sophisticated methods to contribute to see the contribution of those regions in the integration space to the full integral. So it's just a technical
but
problem.
You get a number at the end of the day, you don't.
Yeah, at the end of the day, of course, this is just a number, and whatever you get, you get. So also the continuous solutions just give you some contribution to the index, whose form is more complicated. But anyway, today I want to focus on these specific solutions. So there's this family of solutions, and similarly, you can find solutions, for instance, that are uniformly distributed with a periodicity tau plus 1. So that would be another family of solutions. And so similarly, you would have solutions where all values j are some constant plus j over n, say, times tau plus r for some r. And similarly, there are various other families of solutions. They're easy to find, and they always are guaranteed to exist, again, independently of the deltas and of all these other solutions. So we definitely have, so these are all discrete solutions, and they're also discrete solutions that have two families of eigenvalues, say, separated by 1/2. That you can also prove that also here all the forces cancel. So these are solutions first found by Hung and Liu that also contribute to the index. So there are various families of known solutions of this type that contribute to the index, and those solutions can obviously be extended also to the large n limit, where essentially they just become some continuous distribution of eigenvalues along these lines. So those solutions have a nice large n limit, and it's not clear if the other contributions also have a nice large n limit or not. So today I'll just focus on computing the contribution of these specific solutions. So
you can ask one.
Samir.
Can I go first?
Yes, please.
Yes.
Thanks. Sorry, I'm still confused with this theta function. I thought these beta ansatz equations come from demanding that the shift of the action is 1. And so the way I'm familiar with it, the action has some higher order functions called elliptic gamma functions, which are not modular forms.
Well, these theta zeros are not exactly modular forms. I mean, they're not exactly periodic. I mean, they're related to the theta functions, but they're not precisely the Jacobi theta functions. I mean, they have slightly modified
what you've written in that middle line is exactly the Jacobi theta divided by the Dedekind eta. But I thought the action actually contains like products of two integers, which don't behave like a modular form at all.
No, as far as I know, this is an exact equation for the n equals 4 Supraconformal theory.
Okay.
I mean, I may be using here special properties of n equals 4 Supraconformals. I mean, so this may not be true for a generic theory, but for n equals 4 Supraconformal theory, at least it can be written in this way, yeah.
So this is Benini and who?
I think it appears, I don't remember which paper exactly I took it from, but yeah, one of the recent papers of Benini, and either the paper of Benini in Milan or the paper of Benini and his other student.
Ofer, sorry.
And these Bethe ansatz equations, I mean, they appear in this form in many places.
No, those are fine. I'm not complaining about
okay.
The action itself, the integral.
Right, okay, yes.
Ofer, sorry, I realized that I didn't explain when we chatted about this in the format of the seminar. So we usually have a bit of a break after around 45 minutes, whenever it's convenient, where we sort of chat informally, and then you kind of can go on, for a reasonable length of time.
Good. So I think probably in 5 minutes, I'll finish with the field theory part of the talk, and then that will be a good time for a break. And then after the break, we can discuss the gravity side. So if that's okay with everybody.
Perfect.
So the field theory side is basically done. I mean, in the sense that we have these solutions, and we just have to compute their contribution to the index, and then that will give us the index from the field theory side. So we have these specific known solutions, and then I just need to write down what is the value of the contribution of these solutions to the index. So again, there's lots of mathematics of elliptic functions that goes into it. So again, the index is written. So one of its contributions is the sum over these specific solutions. And we have to evaluate what that contribution is for a given solution of the type that we wrote as a function of the deltas. So it turns out that it's easiest to describe that solution. First of all, I had these solutions where the eigenvalues were spread out with a periodicity tau plus r. So as I mentioned, the index is periodic under shifts of the deltas and also under a shift of tau. Obviously, the shift of tau here permutes different solutions. So I have the solution with periodicity tau, then taking tau to tau plus 1 would give me the same index, but the different solutions would be permuted. While if I take the deltas to delta plus 1, then that does not permute the solutions. I mean, that leaves the solutions the same. So that's how these shift symmetries act on these different solutions. Now, to write the solutions, it turns out that it's simplest to choose specific values of these parameters delta 1 and delta 2, which sit in some specific strip in the complex plane. So by shifting the values of these delta i's appropriately by integers, I can always choose their values such that the imaginary part. Sorry, is there a question? Yeah. So I defined here these two lines in the complex plane with the slope tau going around in 0 and -1. And by shifting these deltas by 1, I can always bring the deltas to sit inside this strip. So we can define delta I tau to be equal to delta I plus an appropriate integer such that it lies inside this strip. And then once we do that, and we also define some, it turns out that, so we choose both of the deltas, we shift them by integers so that they lie somewhere inside this strip. And then it turns out that there are two options. Either their sum also sits inside this strip, or it could sit in the other strip that's adjacent to it, and then we have to shift it also by 1. So I'll discuss here only the simplest case where also the sum lies inside this strip. So in that case, we just define also another parameter delta 3, which is just some other combination of delta 1 and delta 2. And then in terms of these variables, it turns out that the log of the contribution to the index of this specific solution, which has the eigenvalues distributed with periodicity tau. So this is some function of tau delta 1 and delta 2. And it turns out that the log of this specific contribution to the index, well, first of all, it scales like n squared in the large n limit. So of course, that's the right scaling so that we may be able to identify it with a classical gravity solution. And then the specific value turns out to take the following form. So it's a product of this delta 1, delta 2, and what I defined here is delta 3 divided by tau squared. So that's the leading order term if I just compute the residue of the pole for the specific Bethe ansatz solution and expand it in the large n limit. Then there's an extra contribution that's log of n. There's an extra contribution that's order 1, which will not be so interesting for this talk. And then on top of that, it turns out that there are then non-perturbative contributions in this large n expansion. Basically, we know that there have to be some extra non-perturbative contributions because this expression and the way that I wrote it, because of the way that I defined these delta I taus, I mean, so these are not a continuous function of the deltas. I mean, but whenever a delta comes here, then it jumps to go to the other side. So if this was the only contribution, then this would not be an analytic function in the deltas. So there have to be some extra non-perturbative contributions that fix that. And it turns out that the general form of these non-perturbative contributions, so it's a sum over some integers of an expression. So these non-perturbative contributions are exponentially small in e to the minus n. And the coefficient of e to the minus n turns out to be these delta I taus divided by tau times some integer ni. So it looks like with some coefficients that depend on these integers. So it looks like some instanton sum where these ni's for I goes from 1 to 3 are some sort of instanton numbers. And each of these instantons has an action which takes the form of 2 pi n times this delta I over tau. So we have this sum. And the fact that the imaginary part of this is positive, of course, guarantees that these extra corrections are exponentially small. And in principle, we can compute all these coefficients exactly again. All this comes from really explicitly just plugging in these solutions and seeing what they give us.
Sorry, this is asymptotics of the index itself, or is it?
Yeah, so the full index is then given by the sum of this over the solutions. I mean, so we have the exponential of this thing, and then also the contribution from the other solution where this is shifted by an integer. So part of the contribution here is so this includes in particular the sum of r of these exponentials of these i's for tau plus r, delta 1, delta 2, and then there are also contributions from some of the other solutions which I won't write down explicitly here because of lack of time, but they're also known. But, and then in addition to that, there would be the extra things.
Particular family of the Bethe ansatz solutions.
Right. So we take the specific family that's known and which does have a nice large n limit, and which are also discrete and so on. So for that family, we find we compute exactly this sum, and then each of these terms. So we have a sum over the different solutions, and then each of these terms has this expansion where it looks like it has a leading term of order n squared, subleading terms of order 1. Then it has no further perturbative contributions in 1 over n, but it then has these exponentially small contributions, which again can also be explicitly computed. And of course, the fact that it's a part of this of order n, of course, all these different terms the ratio between two different terms here, of course, is e to the minus n squared times something. I mean, so corrections that differ by an action of order n squared may mix with each other, but for each specific term, it's still well defined to discuss its corrections that go just like e to the minus n. So those are the corrections that I'm discussing here and which we computed.
But could I ask how fast the number of solutions grows then? If you have
well, the number of solutions. So in particular, we have this goes from 1 to n. I mean, so the number of these solutions also goes to infinity at large n.
Yeah, but it's particular family. I mean,
right. So that's just this family, but the other families, well, the other known families don't grow faster than this. I mean, so there are other families that involve the partitions of n if you write it as a product, and for each decomposition of n into a product of integers, you have some number of solutions, which is the sum of these two integers and so on. But the number doesn't grow much faster than this, for at least for these known solutions. But again,
so
we don't claim to have a full
saying,
specification.
So I'm basically saying this families of solutions which you consider now, they dominate the large n expansion.
So we don't know that. I mean, so that for that we need to compare to the gravity side. But as far as the comparisons to the gravity side that were made, it seems all the evidence is that indeed these are the solutions that always dominate the large n limit. But again, we don't know that. I mean, there may be other solutions that are also important.
But if you count for n equals 2, 3, and 4. And compare with those families.
Well, but okay, but yeah. So of course, for any finite value of n, all the solutions contribute. I mean, it's only in the large n limit that maybe some solutions are more important than others. I mean, so
yeah, but just which fraction of solutions this family includes out of for small numbers of n?
Yeah. So I think it's only a small fraction of the solutions. I mean, the full number of solutions probably grows like some higher power of n and so on, and maybe even exponentially. And then again, it's not really known. I mean. So there's certainly many more solutions, but it's plausible that these solutions dominate the large n limit, with some caveats that we can discuss later.
Because it sounds like large n is like thermodynamic limit of Bethe ansatz, where you have to consider the gas of the Bethe roots and in principle also some entropy contributions and so on, not isolated solutions.
Yeah, that's right. So we don't have any good arguments that the other solutions don't contribute. I mean, in particular for the continuous ones, because those are it's not even known how to compute precisely their contributions. So there are certainly no good arguments that these are the only contributions, but these contributions are there. And what I'll show in the second part of the talk after the break is that we can map these specific contributions to specific solutions on the gravity side. So these specific contributions seem to match nicely to gravity solutions, and it's not known yet what about all the other solutions.
Okay. Thank you.
So I think if there are no more questions, then I think now would be a good time for a break. So our goal in the second part of the talk will be to ask whether we have this very specific contributions to the index or to the S3 cross S1 partition function. And the question is, can we reproduce this from some sum of gravitational solutions on the other side of the correspondence? Okay. So welcome back. So are there any questions that came up that you do want to share with everybody about the field theory part of the talk before I move on to the gravity side? Okay, so next we move on to the third part of the outline, which is the gravity solutions. So we want to so this index is just the partition function on S3 cross S1 up to some constant that will not play any role in this talk. So we want to find solutions that are asymptotically ADS 5 cross S5 with the boundary that's S3 cross S1, and with some specific chemical potentials on this S1, which translate here to having some specific holonomies of our various gauge fields and the metric, which translate to the values of these parameters here at tau, delta 1 and delta 2. So we need to look for solutions like that. And in general, I mean, there are known black hole solutions that have these holonomies, but the problem is that in general, the holonomies that we're interested in are complex. And in particular, when we look for supersymmetric solutions, it turns out that these holonomies are always that complex. So it's not so obvious what it even means to look for gravity solutions with these real fields of the metric and the gauge fields that have these complex holonomies near the boundary. So that's a general unknown question in ADS-CFT as far as I know how to compute. Of course, in the field theory, nobody stops us from putting in background complex sources for any operators. I mean, that's well defined in the field theory as long as the partition function converges. But in ADS-CFT, we don't really know how to map that to the gravity side. So all that we know how to compute on the gravity side is what happens when we have very real sources. And then the way that people generally deal with these complex sources is to compute, say, the action, say, of the gravity solution for some real values of these sources at chemical potentials, and then to analytically continue that to complex values. So that's also what we'll do here. I mean, so of course, it would be nice if we knew how to do better than that. I mean, and to really do some continuation to complex string theory on ADS5 cross S5. I mean, but because we don't yet know how to do that, then we'll just take the answers and analytically continue them to complex values. And of course, doing that is rather dangerous. I mean, you may encounter some poles, and there may be various other subtleties in these complex continuations, and we'll see that those subtleties will indeed come back to bite us. But for now, that's really the best thing we can do, is just to compute for the solutions when we have real valued solutions, and then continue them to these complex values. Yes.
Also, another difficulty is that analytic continuation of asymptotic is not the same as analytic continuation when taking asymptotics, right?
Yeah, sure. I mean, first of all, we have to analytically continue the full solution. I mean, so we have some solutions here with some complicated metric that's asymptotic to ADS5 and so on. And in general,
because you analytically
complex boundary condition, we have to analytically continue the full infinite dimensional space of these metrics. I mean, at the least.
It's like in usual WKB. You can't analytically continue all the way.
Yeah, right.
Sometimes something which was exponentially suppressed could become important.
Exactly. So that's exactly what we'll see that will happen also in this case. But again, unfortunately, that's the best thing that we can do for now, because we don't have any good rules for computing with complex sources. So that's what we'll do. So we're going to look for solutions that are asymptotically ADS5 cross S5 with these holonomies. And these are just black hole solutions in ADS. So these solutions are known. So we're looking for solutions of type 2b supergravity in principle with these asymptotic boundary conditions. But we can actually simplify things. This has a consistent truncation to a 5-dimensional supergravity with 3 gauge fields and 2 scalars, and that consistent truncation already includes all these solutions with 3 charges and 2 angular momenta and so on. So the way that in practice this is done is people first found solutions to this supergravity, which again you can find for generic values of the chemical potentials and the angular momenta. And then those solutions, you can lift them by explicit formulas to solutions of type 2b supergravity, where you have just the metric and the 4-form field. These are the only fields that are turned on in these solutions. So these solutions are known in the Lorentzian space for these black holes, and then you can continue them to Euclidean space in the usual way and Wick rotate. And in the Lorentzian space, we write these usually as a function of these charges. But when you Wick rotate it to Euclidean space, then it's more natural to view them as functions of the chemical potentials. So you have the usual thermodynamic relations between these charges and some chemical potentials for the angular momentum and for these 3 different U1 symmetries. And in the Euclidean solutions, these chemical potentials show up as the holonomies of the gauge fields near the boundary in the standard way. So given these black hole solutions, so these black hole solutions are known, and if we want, we can deal with them in 5 dimensions or lift them to 10 dimensions. So we have known black hole solutions with various values of these chemical potentials. And these chemical potentials, if we just compare this to the form of the index, which I guess I already erased, then you can just compare which values of the chemical potential correspond to which values of the parameters of the index. So for instance, this tau parameter, computing for the gravity solution, it's related to these angular momentum chemical potentials by some formula like this, so omega 1 minus 1. And similarly, you can compute delta 1 and delta 2 on the gravity side just by looking at the solutions and by looking how they behave near the boundary. So we can look at the known solutions. Again, I won't give you all the details of the solutions because of lack of time, and they're not too illuminating. I will mention that on the gravity side, a priori, we have these 3 U1 gauge fields. So we have these 3 chemical potentials, delta 1, delta 2, and delta 3. But if we're looking for supersymmetric solutions, which are the only solutions that we expect to contribute to the index, and then those chemical potentials obey some relations, which is actually take exactly the same form as this relation for delta 3 that I defined on the field theory side. So they obey a relation that 2 tau minus the sum over these deltas has to be equal to 1, at least in one branch of black hole solutions. So these solutions have, the supersymmetric solutions have the same number of parameters. And then we can compute the action of these solutions just by the standard methods of computing the gravity action. I mean, well, there are many different ways to do that, which I won't go into. So people computed the action of these solutions as a function of these chemical potentials. Again, we're just looking now at tau equals sigma, delta 1 and delta 2, and delta 3, which is determined by this equation for the parameters on the gravity side. And people found, just in classical gravity, an expression which looks very similar to the expression that we found for the log of the index. Namely, they found n squared times I pi times the product of these 3 deltas on the gravity side divided by tau squared. So it looks very similar to the expression that we had on the field theory side. Let me just mention that again, the way that this was actually computed was not by taking these complex values of the, in particular here, it's obvious that if tau is complex, then also these deltas have to be, at least some of them have to be complex. So this was not computed for these complex values. This was computed for real values from real solutions whose action we know how to compute. And then it was analytically continued in these parameters to these specific values which we're interested in and which preserve supersymmetry. So by that method, people got from gravity this expression for the action of the gravity solution. And of course, people notice that this is exactly the same. If we take e to the minus this action as the contribution of the gravity solution, then that's exactly the same as what we found from the index if we identify these parameters on the gravity side with the parameters on the field theory side. So so it looks like a priori, it looks like we have this match here, and everybody is happy. So so that's what you find at first sight of looking at the gravity solution. But if you try to look at things in a bit more detail, then you find that actually things don't work so nicely. And the reason that things don't work so nicely is that here on the gravity side, these parameters delta I, they really come from the chemical potentials of these black hole solutions, which are related to the charges of these solutions. And on the gravity side, these delta I's don't necessarily lie inside this strip that we had on the field theory side. So on the field theory side, we got this expression for the index only when these delta I's lay inside this specific strip in the space of all possible chemical potentials. While on the gravity side, we find this expression for any values of the delta. And of course, related to that, the expression that we find on the gravity side is actually not periodic in these deltas. So on the field theory side, of course, the index is completely periodic in these deltas. On the gravity side, if you just look at a specific gravity solution with specific charges, then its contribution is not periodic in these deltas, but it's just given by this expression. So essentially, the reason is that, well, different values of delta correspond to different charges of these black holes, which give us different solutions. Now, the holonomy of the gauge field in some specific gravity solution would go like e to the 2 pi I times this delta. So different solutions whose deltas differ by an integer would give us exactly the same holonomy, so they would contribute to the same index, but the gravity solutions are actually different. And solutions with different deltas, they would all contribute to the same index because they all have the same holonomy, but they contribute these different expressions which depend on these delta I's in this way, even when the deltas are not inside this specific strip in the parameter space. So in other words, if I really take seriously the contribution of all these black hole solutions to the index or to the partition function now on the gravity side, then what I would find on the gravity side is that if I'm looking for all the contributions that have some specific holonomies near the boundary, then I don't just get this expression, but I also have solutions corresponding to all the shifts of these chemical potentials by any integer. All of those solutions also have the same holonomies, so they have exactly the same boundary conditions on ADS5 cross S5. So what I would actually find on the gravity side is that instead of having a single solution that just gives the exponent of this, I find a 4-parameter family of solutions, which would give a contribution, which is this function, but with any possible integer shift, both of this tau. This tau can be shifted in a similar way, and I would still find a gravity solution with exactly the same boundary conditions. Sigma can be shifted by an integer. This delta 1 can be shifted by another integer, and so on. So on the gravity side, it actually looks like we have too many solutions with specific boundary conditions. And one of these solutions, if the delta I's happen to land in this strip, then one of these solutions really matches with the Bethe ansatz solution on the field theory side. But the other solutions give me completely different answers. So it looks like there is this mismatch with the field theory. Or more precisely, we saw also on the field theory that we had a sum of solutions where tau was shifted by an integer. So these solutions, if I shift tau by an integer and sigma also by the same integer, that does correspond to the same sum that we had also on the field theory side. So one part of the sum does exactly match with the sum over these different Bethe ansatz solutions that we had on top there. But the other 3 sums that we have here, they lead to completely different expressions, which we do not have an analog for in this Bethe ansatz expression. And moreover, it turns out that things are even worse. It turns out that in many cases, these shifted solutions actually dominate over the solutions that we do have. So it looks like if we would really treat seriously all these gravity solutions and include the contributions of all of them, then we have too many solutions and they give us the wrong answer. So at the level of just naively treating these gravity solutions and summing the contributions of all these different solutions, it seems like we have a mismatch. even though a specific solution does look very similar to this index, but the sum over all solutions is definitely not the same as the sum over all the different solutions to the index.
Sorry, a bit naive question. If you start without all this Bethe ansatz solution, start from index formula and I don't know, compute by your favorite method, this integrals, and then it gives some number. Will it match any?
Well, so the number that you get, so if you compute it, say by a saddle point, then the answer that you get depends on the values of the chemical potentials. I mean, but for many values of the chemical potential, there is a specific saddle point that dominates, and that saddle point will correspond to just one of these solutions. I mean, so doing it this way will just give you one of these solutions. So then you will just get the exponential of that, and of course that will also correspond here to one of these black hole solutions. But in general, there would be other solutions that, from this point of view, would dominate over it. I mean, so if you really include all of these solutions, then you definitely get the wrong answer.
Sorry, Ofer, just a quick precision regarding what you said on this delta parameter match on the field theory side. I think because I'm having this in relation to this, if you take this integral, like you said, by saddle point approximation, and there is no specific identification scheme, like you say, to find the deltas in terms of the chemical potential and the momentum for them to be not just identified uniquely, but as some combination to lie in this complex strip. But you say that this is still not sufficient to find the match on the gravitational side, right?
Well, what I was saying that if you try to do if you try to take the saddle point, if in some specific region of the chemical potentials, if you would try to do this for deltas, I mean, of course, I mean the index is just periodic under these deltas. I mean, so from that point of view, of course, it doesn't matter if they're in the strip or not. I mean, you would find the same saddle point independently of whether they're in the strip or not. But what I'm saying is that the expression for the value at that saddle point is most simply written by shifting these deltas to be inside the strip, and then it would take this value. So that's what people found when they did these saddle point evaluations of the index.
I understand, but to match that on the gravitational side, like you need to understand how somehow to fix which solutions should not, like you said, not to over dominate the ones that you
exactly. So it looks like we have here too many solutions, and something should be wrong with some of these solutions, and presumably that's related to this naive analytic continuation that we did, where we just assume that we can just analytically continue the value of any solution into the complex plane and get a sensible answer. But we'll see in a few minutes that indeed most of these solutions should be discarded, and we'll end up with just the right solutions.
Okay.
Okay, so we have this problem, and the other problem that we have here is that so far we don't really see these. Well, in principle, we could try to see the perturbative corrections and these non-perturbative corrections, and the other question would be, can we also find these non-perturbative corrections from the gravity side? So instead of dealing directly with this issue of too many solutions, let me now discuss how we see the non-perturbative corrections, these exponentially small terms, from the gravity side, and it will turn out that that will also help us to understand the first problem with the fact that we have too many solutions. So what's the topology of these solutions? I mean, so these solutions, they're asymptotically ADS 5 cross S5. So asymptotically, we have this S5, the S3, and the S1 in the solutions. And if we look at black hole solutions, then of course, typically the S1 shrinks to 0 size at the horizon, and then these other manifolds do whatever they do in the interior. So topologically, the solution looks like something like this. Of course, it's not a direct product. I mean, there are many mixing terms between all these different solutions. But topologically, it looks something like this. And then we want to identify where do these non-perturbative contributions come from on the gravity side. So as we mentioned, these non-perturbative contributions, they go like e to the minus n. And the natural place on the gravity side to find terms that are exponentially small in n is from D3-branes, because in the ADS CFT correspondence, the tension of D3-branes, which goes like 1 over G string L string to the 4th, is exactly proportional to n in units of the ADS radius. So wrapped D3-branes naturally give contributions that are proportional to n. So they would give terms that are exponentially small in n. And it turns out that indeed in these solutions, you can find BPS D3-branes that sit on the horizon of the black hole, and that wrap an S3 inside this S5 and an S1 inside this S3. So there are BPS solutions like this for the D3-branes. And so in general, these preserve supersymmetry. So they would also contribute corrections to the gravitational action of these solutions. And then if we compute the action of these D3-branes, so of course we just compute that by the standard methods of computing the action with the contributions from the metric in this black hole solutions and from the four-form field and so on. So we have to compute this, and so you plug in these solutions, and what you find turns out to be that for this say for specific D3-brane wrapping on one of these S3s and one of these S1s, you find that its action is given by 2 pi n times these delta i's on the gravity side divided by tau. So that when you compute the action of these solutions, then their contributions turn out to take exactly this form that was expected from the field theory side. So this is exactly the same form that we found also for the exponential corrections on the field theory side. So it looks like these D3-branes indeed nicely explain these non-perturbative corrections that we found on the field theory side, except that there's still this extra caveat that on the field theory side, the expression that we had was either the 2 pi I n times delta I shifted into this interval divided by tau, while on the gravity side, we don't have this periodicity, so we just find this expression for general values of delta and tau. So sorry, this was very quick because it's getting late, but are there any questions about this before I discuss the interpretation? Okay. Now, if you remember, going into this interval in particular meant that we need to go to this interval so that the imaginary part of delta I equals tau will be positive. Now, on the gravity side, generally, the imaginary part of this delta I over tau could also be negative. And if it's negative, then what that means is that these D3-branes actually give us exponentially large corrections to the action instead of exponentially small corrections. Of course, we're used to the fact that in supersymmetric settings that cannot happen. I mean, usually if you have a supersymmetric brane, of course, it must have a positive contribution to the action. But once we do these continuations to complex variables, then it seems that that logic breaks down. And in these complexified solutions, it turns out that even if they're supersymmetric, it turns out that wrapped D3-branes can actually give exponentially large contributions to the actions. So schematically, what seems to be going on is that, suppose that we had some function of a real variable that had a large n expansion that looks like e to the n squared times some function, and then that would have some perturbative corrections, and on top of that, we may have some non-perturbative correction that say would go like e to the minus n a squared, mimicking the effect of these 3-branes. So suppose that our partition function as a function of some real variable a had this value. So a priori, of course, we'd be happy with this type of expression, and we'd interpret this as perturbative corrections and non-perturbative corrections. But if we would then try to continue this into the complex plane, then once we continue to a regime where the real part of a squared is negative, then these corrections would suddenly become large. And then, of course, this whole expansion would break down and not make sense anymore. And in particular, it wouldn't make sense to treat this leading order value as the value of any sensible solution. So that seems to be what's going on also here. So it seems that when we do this analytic continuation, at least in some of these solutions, in particular the ones where this condition is not obeyed, then it looks like we're definitely doing something wrong because we find that the contributions from these D3-branes actually dominate over the original solution. So our interpretation is that in this case, this analytic continuation was not justified, and our conjecture is that if one correctly does the analytic continuation from real to complex values, then these solutions where the D3-branes give exponentially large contribution should all be thrown out, and we should only keep those contributions for which all the D3-branes actions have a negative or a positive real part to their contribution to the action, so that they give exponentially small rather than exponentially large contributions. So it turns out that if we do that, so if we impose on this 4-parameter family of solutions that we had, so if we impose on this 4-parameter solution that we had here, if we impose that we only keep those solutions where the real part of the D3-brane action is positive, such that, sorry, I guess, well, where the D3-branes contribute exponentially small rather than exponentially large contributions, I guess I actually want the imaginary part to be positive for that, because here the contribution goes like the I times the D3-brane action. So if I only impose that I only keep those solutions where all the D3-branes obey these contributions, then it turns out that this sum is exactly restricted to exactly the same sum that we had on the Bethe ansatz side. So this restricts the sum exactly to the values that n1 is equal to n2, so that we have exactly the same shift in tau and in sigma, and the other shifts have to vanish if we start from values of deltas that are inside this strip. So that just imposing this condition restricts the sum exactly to the same sum over Bethe ansatz solutions that we had on the field theory side. So with this caveat that we don't know how to derive that indeed for complex values we should only keep these solutions, but it seems like a sensible assumption. So with this sensible assumption, we find a precise match between what we get from the black hole solutions And what we got from the Bethe ansatz sum over solutions, where that matching extends not just to the perturbative terms in N, but also to these non-perturbative terms. I mean, so we didn't match precisely the coefficients of these terms yet, but at least the exponentials of the exponentially small corrections on the two sides exactly match. So in that sense, we have here a very high precision test of the ADS CFT correspondence.
Could I ask, so instead of analytically continuing already asymptotic limit of supergravity, and one analytically continuing the quantum expression, the exact integral?
Sorry, I'm not sure if I understood. Can you repeat the question?
Well, I mean, so in the gravity, you had to analytically continue into the complex plane. But if you keep it real in the gravity, but do instead analytic continuation in the quantum expression for the index.
Well, the problem is that on the gravity side, I mean, on the gravity side, it turns out that all the supersymmetric solutions always have complex values for at least some of these chemical potentials. So I can't. So there's no real value where I can really match it directly to the field theory. I always have to do some analytic continuation, and then I always run into these problems that for any analytic continuation that I do, at least some of the solutions will have these large non-perturbative corrections. So I must impose this restriction, and after I impose it, then I do find a precise match. But yeah, it would be nice if there was at least one value where we did have real solutions on the gravity side so that we could know better what we're doing. Yeah, but that turns out not to be the case, as Samir and his friends showed a few years ago. So basically, this is the end of the talk. I mean, so after all these song and dance, then we do find a very precise matching between the gravity side and the field theory side. Let me just mention that this matching was for the solutions where we looked at one group of eigenvalues in the complex plane. There are also these other solutions I mentioned where we have several groups of eigenvalues equally distributed on the complex plane. And for those, we can also contribute precisely their contribution to the Bethe ansatz. And it turns out that these other solutions, if we have here m groups of these eigenvalues, then those solutions turn out to map to ZM orbifolds of these ADS black holes. And again, we can precisely match the contribution to the action, both of the perturbative and the non-perturbative contributions of these orbifolds. We can precisely match them to the contributions also of these Bethe ansatz solutions. So really, for all of the known Bethe ansatz solutions that have a nice large limit, we have, for each one of them, we have a very specific gravity solution, which obeys these requirements that it's self-consistent to include it, even for complex values. And both the action and the non-perturbative corrections of these gravity solutions exactly match to the field theory side.
So I probably said that. Yes. So you can always find a regime where only one of beta solutions dominates. This
right. So of course, all these solutions have an action proportional to n squared. I mean, so generically, one of them would dominate over the others. But the one which dominates can change when I move into different regimes. So there are some regimes where the first solution dominates. If you change the chemical potentials, another one would dominate. And then there are other regimes where these orbifold type solutions dominate. And then there are yet other regimes where none of the solutions dominate because there are many solutions that have the same real part. So there are different situations. But again, for our purposes, that's not so important. I mean, we really see that we can exactly match each of these Bethe ansatz configurations to a gravity solution. So at least that part of the index we can reproduce directly from the gravity side, including both the perturbative and the non-perturbative contributions.
I ask a naive question. So from the gravity side, where does the -1 to the f enter, and how complicated it will be to do the honest computation without the -1 to the f?
Well, the gravity side, there's no -1 to the f. I mean, of course, if there was, I mean, the gravity side, we're just taking the classical action of these black hole solutions without any signs. Of course, if there is a sign, then it would just be a shift by I pi here, which is over order 1 and not over order n squared. So if we were trying to do the matching, including also the order 1 terms, I mean, we didn't try to match the order 1 terms in the index. So it may be nice to match the order 1 terms in the index, and then it may be important with which sign we include these different gravity contributions. But as long as we're just matching the order n squared terms, which is all that we did so far, then that doesn't really show up on the gravity side. Because on the gravity side, we just have these discrete solutions, and their action goes like n squared.
So maybe my question is, how different do we expect the partition function without the -1 to the f to be from this index? It's strong coupling. I thought it should be totally different because.
Yes. Yeah, of course. Then it would count the full, not just the BPS states, and it would count everything. And that we know that it does depend on the coupling constant, right? In particular, then it does not depend on the coupling constant, but the thing that you want without the -1 to the f would depend on the coupling constant. And we can compute it at weak coupling, but I have no idea how to compute it at strong coupling. Of course, we can compute it from the gravity side. So on the gravity side, I do know many black hole solutions. We can sum them, but I don't know how to compute it directly in field theory.
No, it doesn't make sense.
So I mean, the matching that you're doing is really the best thing we can do for now with the current knowledge.
Yes, okay.
But as you said, the gravity side doesn't care whether you compute index or the true partition function, right? So it means
well, but on the gravity side, I did include only supersymmetric solutions. I mean, so my sum here on the gravity side, I did count only 1/16 BPS solutions. So I looked only at those values of the chemical potentials which were supersymmetric. But you're right that on the gravity side, of course, I could also choose any other chemical potentials which would break supersymmetry and then similarly compute what I would get from them. So maybe there would be some more complicated expressions. I mean, these expressions do simplify a bit when they have supersymmetry. So there are slightly more complicated expressions. But you're right that on the gravity side, I can also sum non-supersymmetric black holes. But that I don't know what to match to on the field theory side. I mean, so that's,
but in the field theory, I could also just sum over 1/16 BPS, but not weight them with a sign, right? That should be another computation.
No, in the free theory you could, but there's no reason why that should be the same as in the strongly coupled theory. It's only with the sign that it's protected under.
No, but then the prediction is of that it will be the same at strong coupling. Pedro?
Yeah.
Right. So it would not be protected, right?
Right.
So it would not be protected.
So that's why I don't know how to compute it. So I don't know how to compute that thing at non-zero
coupling. But at strong coupling, you know, and at weak coupling, you know, right?
Well, strong coupling, we can try to compute it from gravity, but again, in gravity, there are all these caveats. I mean, so I wouldn't necessarily know what exactly are the rules, but yes, in gravity, in principle, I could compute it.
In gravity, it's the same as what you did, right? Because you don't see the -1s.
Well, it's the same as what we did, except that the question is which solutions should I keep and which ones should I not keep if I have complex chemical potentials.
Right.
I mean, so you would run into all these problems, and I'm not sure. So there are various subtleties, but in principle, I can compute it. That's right. But I don't have anything to compare it to on the field theory side.
So in the field theory side, you know that although a priori it's much more complicated, at strong coupling it should be again similar somehow.
That's right. Although the expressions without BPS are more complicated than this formula. I mean, this formula is just for the BPS case. Otherwise, the formula is more complicated, but it could still be computed. It's still an explicit function that you can write. So there is a strong coupling prediction for the density of all states. Yes.
No, but I'm not proposing to sum over more than half to more states. I'm saying sum over the same states, but don't put a -1 to the f.
Yeah, sure. So yeah, right. So so that would be exactly the same on the gravity side as strong coupling. Yes.
Right.
Yeah. So sorry.
But at weak coupling, do you have a way of putting instead of a -1 to the f? Yeah. You don't know because
only at zero. At zero coupling we can do that. Yeah, at zero coupling we can do that, but not at any non-zero value of the coupling because I mean the pairs of multiplets join together, and I don't know exactly how.
Then the difference will appear at one loop, right? Because determinants around this gravity solutions won't cancel, so that's where the difference begins. Supersymmetric and non-supersymmetric version of the same index.
Right. Yeah. That's exactly these are the one contributions to this exponent. That's right. Yes. Exactly.
So just fermionic and bosonic boundary conditions will break. Will not allow.
That's right. Yes. So let me summarize. I mean, so this is basically the end of the talk. So on the field theory side, we analyzed the large limit of the index using the Bethe ansatz. We found some specific solutions which we could understand at large n and compute their contribution at large n, and we found very explicitly what they contribute. And then on the gravity side, we found that if we naively do an analytic continuation of black hole solutions, then we don't precisely match with that expression. But if we do it more carefully, taking into account that some of the continuations give us unstable solutions where the non-perturbative corrections to a solution would be larger than the original solution. So once we make this rule that we should throw out all these unstable solutions, then we do find a precise match between all the remaining solutions and the solutions that we have on the gravity side. And again, these includes both the black holes and the orbifolds, and it includes all the known stable solutions on the gravity side mapped to all the known solutions for the Bethe ansatz that have a nice large n limit. So obviously there are many directions to continue this. It would be nice to understand more generally what are the rules for doing ADS-CFT with complex background fields in general and for black holes in particular. It would be nice to extend this matching also to the order 1 terms and to the other non-perturbative corrections to these coefficients for these terms. It would be very nice to understand the contributions from the other solutions to the Bethe ansatz, in particular from the continuous family of solutions. And these may or may not be related to additional contributions on the gravity side. So that's something that's still currently being investigated. it would be nice to generalize the analysis. So there are many possible generalizations of the analysis that we did. So let me just list a few of them. So we did the analysis so far just for this case of sigma equals tau, but one can generalize it to sigma not equal to tau, where the Bethe ansatz formula is slightly more complicated. One can generalize this to many other theories with less supersymmetry. So of course, the index makes sense for any 48 equals 1 theory. And in particular, for any 48 equals 1 theory, you can still use this Bethe ansatz method and try to get a very precise matching across the ADS-CFT correspondence. So that should be possible. In other dimensions, I mean, we don't have the analogs of these Bethe ansatz expressions for the index, but at least on the gravity side, also in other dimensions, people often do continuations to complex fields. And it would be nice to see also in black holes in other dimensions, like in ADS4, do we have similar non-perturbative contributions coming from wrapped branes? And can we understand what they contribute on the field theory side? And well, and then there's the big question that I didn't discuss at all in this talk is, does this teach us anything about microstates? I mean, so of course, eventually understanding better this index and what it looks like on the gravity side should also help us to understand better the black hole microstates. But on that, I really have nothing to say so far. So that's it. So thank you very much. And sorry for going 1 hour over time almost.
Thank you very much. Let's thank Ofer for the great talk.
I broke my finger. I can't clap.
Are there more questions?
Yeah.
Ofer,
well, I mean,
just to understand these D3-branes, sorry.
Yes.
Can I go back to a flat space limit and then take a near horizon? Or
for these D3-branes?
No, you know, so I start with my original
horizon limits of flat space black holes. I mean, so.
So I just meant, you know, if I have a stack of D3-branes that gives me my ADS space, these D3-branes are somehow.
No, well, that already doesn't work. I mean, here it's important that we're in global ADS. I mean, so we're talking about the field theory on F3. So already that I don't know how to get from any near horizon limit of branes. And then these D3-branes would sit on top of that space. So yeah, so I don't know any interpretation of this in terms of any near horizon limit of D3-branes, I'm afraid.
Yeah, because they are very strange. And I mean, because there are other d-instantons, right, that are a little bit more natural, at least in normal ADS space.
Well, but these preserve, of course, the thing about these is that they preserve the same 1/16 supersymmetry as the full background does. So for that, I think no other D-branes do that. I mean, there are other D3-brane solutions that also preserve 1/16 supersymmetry and that we're currently analyzing in our work in progress. But I don't think any other type of D-brane.
So the d-instanton
supersymmetry. So the instantons in particular break these supercharge completely.
Okay.
Well, you could sort of see that because the D3-brane, because those would also have an action that depends on G-string, and of course we're converting it to an expression in the index that's independent of G-string. So they'd better not contribute, and indeed you can show that they're not.
That was the question.
It's only the D3-branes that happen to have an action that's exactly proportional to n with no powers, with no factors of the coupling. So those are the only ones that could possibly contribute to this index.
Yes, but it would. Yeah, okay, but you have a more direct argument. Yeah.
Yeah, of course you could directly check supersymmetry and see that it's only those that preserve it. Sure, but I could have guessed that from the beginning just on these general grounds.
So I have more like a comment. So I mean, probably for many of us, it's reminiscent of what happens in quasi-classical limit of strings in EDS5 when you have classical limit of beta ansatz solutions. Also, number of beta roots increases, and then at the end, you also have classification of classical solutions of the string in terms of algebraic curve, and then you can match these two interpretations exactly. So I wonder whether there is some algebraic curve description of the general set of more general set of solutions in supergravity.
Yeah, so that would be great, of course. Yes.
Are there more questions?
I have one question about your formula. If I understand correctly, for 1/8 BPS states, the coefficient in front of n square vanishes. Is it correct?
That's right. Yes.
Is it C?
Well, I mean, I don't think. I mean, this index it doesn't. I don't know how to transform it into something that would only count the 1/8 BPS states. I mean. I'm not sure if there's any specific value of the index where only those would contribute. I mean, I think you would have to impose some extra restriction on the states to get only the 1/8 BPS states. And of course, on the gravity side, if you try to construct solutions like that, then they would just have 0 horizon area, so you'd see that immediately. But on the field theory side, I'm not sure how to relate the counting of the 1/8 BPS states to the index. Is there a way to do that? I don't know.
Okay.
More questions?
Sorry, Ofer.
All right,
maybe I can make quickly, Kolya. So
sure.
Yeah. So regarding this, it's probably an important question. I'm just wondering, maybe it is also related to what Nikolai was asking. When there is a possibility to take a certain type of asymptotic or even maybe thermodynamic a version of this Bethe ansatz, and do you see is there a possibility to relate from this perspective to this to identify contributions that would correspond to the actually counting the microstates? So I'm just wondering if there is a possibility to extract this information, because there is also an exactly analogous this question of how in certain D3-brane setups, if one can use this superconformal or conformal index for the microstate count and for the entropy identification.
Right. Yeah, so we actually discussed this a bit during the break before, and I think the Bethe ansatz is sort of the worst way to do that, because in the Bethe ansatz, if you look at a specific solution, then it doesn't look like a sum over microstates. I mean, it would have non-integer powers of the chemical potentials and non-integer coefficients and so on. So I think that's not the right way to approach the microstates. I mean, for that you really need the sum over all of these solutions, and so yeah, so I don't know how to use this method to learn directly about microstates, but of course the sum over all the solutions does have all the nice properties, and that does give the same over microstates. But yeah, how do we learn from that about the microstates? That's the big question that I don't know.
Yeah, exactly. Because to identify this set of states that you would actually need to filter, I'm just wondering if there is this asymptotic limit. But yeah, okay.
Yeah. So I don't know.
Sorry, Ofer, maybe a very small comment. Just to that's a precision, rather. When you mentioned the difference on the field theory side, suppose you take this, I take this integral by the to superlocalize or to superlocalize on the S3 cross S1, and eventually, as you said, goes to the partition on the circle.
Yes.
But this essentially gives you an exact result, but it does not provide you an exact match later with the gravity in comparison to what you provide, like for each perturbative or leading and non-perturbative parts, right?
Why not?
I mean,
of course, there are all these overall constants that I throw away. I mean, which you would get from holographic normalization and all that. I mean, so are you referring to those, or?
Yeah, partially. I mean,
so of course, there is a long song and dance there that I completely neglected, and so on, in terms of exactly how you normalize these different contributions to the partition function, both on the field theory side and on the gravity side. I mean, but essentially, for the purposes of this talk, it's sort of enough to just normalize the index such that the identity state gives you just a 1 or whatever, and to normalize on the ADS side to normalize it so the thermal ADS just gives you 1, and that sort of fixes all these shifts and so on. And then once you do that, then we have this matching that we described. But of course, the constant terms also have very interesting interpretations and so on that I did not discuss here.
Yeah. I was just thinking on how strongly you depend on the index computation on the field theory side to get these matches if you super localize.
Yeah. Well, I mean, so
you can do that, but probably you don't have this separate piece information like you have been describing. For term-wise, I think.
Mm-hmm. Yeah, maybe.
Okay.
All right, I propose maybe we stop official part now, and I mean, if the people still interested, if there is someone to answer questions, we can continue. But let's thank the speaker again.
Okay, thank you.